Did you know that to uncover its own origins, humanity carried out a dangerous heist nearly 2 billion kilometers from Earth? On that journey, NASA's OSIRIS REx mission shadowed the asteroid Bennu for years, daring to touch down on a crumbling world slowly tearing itself apart under relentless sunlight, all to bring back pristine samples never contaminated by Earth. The moment of contact nearly turned catastrophic when Bennu's surface behaved like liquid sand and almost swallowed the spacecraft. Yet the outcome exceeded every expectation. More than 120 grams of ancient material containing water, clay minerals, amino acids, nucleobases, and even pre-solar grains. Clear evidence that the fundamental ingredients of life were formed in space long before Earth existed. This was not just a scientific mission, but the first time humanity truly touched its own cosmic ancestors. Up next, we will explore why humans are literally made of stardust, and how this journey is leading NASA toward even greater mysteries and dangers, including the asteroid Apophis. Over 200 million miles from Earth, deep within the crushing silence of the vacuum, the most audacious heist in human history was underway. The intruder wore no mask and possessed no heartbeat. It was a construct of aluminum, titanium, and sophisticated circuitry named OSIRIS REx. Its target was not a vault of gold bars or ancient diamonds, but something infinitely more valuable, a substance that humanity has coveted for centuries, yet never truly possessed in its pristine form: dust. But this was not ordinary dust swept across a desert floor. The object of this surveillance was Bennu, a darkened, tumbling mountain of debris, a time capsule, hermetically sealed since the violent dawn of the universe. Bennu is a silent witness, a primordial relic that has existed since before the Earth itself was fully formed. For 5 billion years it has drifted through the eternal dark, guarding within its craggy exterior the frozen chemical fingerprints of our own origins, secrets locked in ice, and carbon untouched by sunlight or human hands. To crack this celestial safe which hurtles through the void at tens of thousands of miles per hour, NASA could not simply knock on the door. They engineered a mission spanning 7 years, a high-stakes journey through the shadows, to stalk orbit and ultimately execute a touch-and-go maneuver to snatch the evidence. While previous missions had collected samples from the coma of comets or imaged asteroids from afar, OSIRIS REx was tasked with a singular, unprecedented challenge to physically touch the surface of an asteroid and bring a piece of it back home. This little heard-of mission was instrumental in advancing our understanding of a time before our planet existed. But why risk so much? Why spend billions of dollars and wager the reputation of global science just to retrieve a handful of gravel from a wild, spinning rock? The answer lies in the limitations of what we can learn from the ground. To the uninitiated, the solar system appears generous with its secrets. Meteorites, fragments of asteroids and comets bombard our planet, daily delivering free samples of the cosmos right to our doorstep. Museums are filled with these charred rocks. So why spend nearly a decade and $1 billion to catch one in space? The answer lies in the rigor of forensic science. To a cosmic detective, a meteorite found on the ground is compromised evidence. The moment a space rock hits our atmosphere, the chain of custody is broken. Friction transforms it into a fireball, subjecting delicate chemical compounds to searing temperatures that fundamentally alter their structure. If that weren't enough, the moment of impact introduces a second, more insidious problem: contamination. Earth is a biological riot. It is teeming with life from the bacteria in the soil to the very air we breathe. When scientists find amino acids, the building blocks of life on a fallen meteorite, they face an impossible question. Did this biology originate in the depths of space, or is it simply terrestrial pollution picked up upon landing? To solve the cold case of our own creation, we needed evidence that had never breathed Earth's atmosphere. We needed a pristine sample hermetically sealed in a vacuum, protecting its secrets from the moment of extraction until it reached a clean room in Houston. This was the mandate of OSIRIS REx. Part of NASA's elite New Frontiers program, it stood on the shoulders of giants like Juno and New Horizons. While Japan's JAXA had heroically paved the way with the Hayabusa missions, OSIRIS REx represented NASA's first attempt to tag an asteroid and bring a piece of it home. The target Bennu was chosen for its primitive nature. As a carbonaceous asteroid, it is a relic from the solar system's formation, a potential bearer of the original organic slurry that may have seeded life on Earth. The stakes were absolute: bring back the black box of the solar system, or return empty-handed. On December 3, 2018, after a 2-year chase across the void, OSIRIS REx finally pumped its brakes and arrived at its destination. From a distance of 1.9 billion kilometers, the navigation team had guided the spacecraft to a precise rendezvous point just 20 kilometers from the asteroid's surface. In the mission control rooms, anticipation was electric. The team thought they knew exactly what they were flying into. Years before launch, scientists had tirelessly trained radar dishes on Bennu to create a shape model. These simulations painted a comforting picture, a relatively smooth, spherical world, likely covered in fine-grained regolith sand and gravel that would be easy for the spacecraft's sampling head to ingest. The engineering parameters for the touch-and-go tag maneuver were designed around this assumption, requiring a safe flat parking lot, roughly 50 meters wide, to conduct the sample collection. But as OSIRIS REx beamed back its first high-resolution images, the illusion shattered. The radar prediction had been accurate in shape, but catastrophically wrong in texture. Bennu was not a smooth expanse of cosmic beach. It was a chaotic, treacherous rubble pile, a loose agglomeration of rocks held together by nothing more than microgravity and silence. The surface was a field of jagged shrapnel, littered with monstrous boulders that defied the team's worst-case scenarios. Some of these rocks were the size of horses, others were leviathans measuring 58 meters across and 20 meters high, roughly the size of a football field. The reality was disorienting. The smooth ponds of dust that the engineers had bet the mission on were nowhere to be found. Instead, the spacecraft looked down upon a rugged, boulder-strewn nightmare that resembled the chaotic surface of the asteroid Itokawa visited by JAXA's Hayabusa, but on a much more threatening scale. The mission planners realized with dawning horror that the 50-meter clear zone they needed simply did not exist. The entire asteroid was a hazard zone. The friendly target they had launched toward had vanished, replaced by a hostile rocky beast that threatened to destroy the spacecraft if it dared to get too close. To understand why Bennu presented such a hostile face to the OSIRIS REx cameras, one must look past its geology and stare directly into the physics of its existence. Bennu is not a solid monolith. It is a rubble pile, a loose collection of rocks and void space held together by its own tenuous gravity. But it is the asteroid's shape that betrays the violent, invisible forces acting upon it. Bennu is not spherical. It is shaped like a diamond or a spinning top with a pronounced bulge of material gathered along its equator. This distinct geometry is the physical scar left by a phenomenon known as the Yorp effect, Yarkovsky-O'Keefe-Radzievskii-Paddock effect. In the vacuum of space, sunlight is not merely illumination, it is a physical force. As the sun beats down on Bennu's uneven dark surface, the asteroid absorbs heat. As Bennu rotates, and that heated surface turns toward the cold darkness of space, it releases that thermal energy as infrared radiation. This release acts like a microscopic thruster, a photon engine that over millions of years exerts a tiny but relentless torque on the asteroid. This solar pressure has been slowly spinning Bennu up, acting like a cosmic hand twisting a top. The OSIRIS REx team detected that this rotation is speeding up very gradually over time. As the spin accelerates, the centrifugal forces generated begin to rival the asteroid's incredibly weak gravity. This internal war between gravity pulling in and rotation pushing out has caused the loose regolith to migrate from the poles toward the equator, building up the ridge that gives Bennu its diamond shape. But the violence of this process is not limited to slow geological shifting. OSIRIS REx discovered that Bennu is an active asteroid, a rare classification. The spacecraft's cameras captured startling evidence of ejection events where the surface of the asteroid seemed to explode in slow motion, flinging rocks and particles out into the void. While some of these rocks escaped into deep space, others were captured by the asteroid's gravity orbiting Bennu as temporary satellites before raining back down onto the surface. These ejections are the death rattles of a world tearing itself apart. The physics dictate a grim future. If the Yorp effect continues to accelerate Bennu's rotation, the centrifugal forces will eventually overcome gravity completely. The equator will shear off, and the asteroid will undergo rotational fission, disintegrating into a cloud of shrapnel. Bennu is not just a destination, it is a dying world spinning itself into oblivion, and it was onto this unstable exploding powder keg that NASA intended to land a billion-dollar spacecraft. Faced with a surface that looked more like a demolition site than a landing pad, the mission planners were forced to scrap their original playbook. The luxury of a 50-meter safety zone had evaporated. Instead, the team spent a grueling year carefully mapping the asteroid's chaotic geography, searching for any break in the armour of rocks. They eventually narrowed the options down to 4 small sites, naming them after birds, to match the avian theme of the mission: Osprey kingfisher sandpiper and the ultimate choice nightingale. Located inside a relatively young crater high in Bennu's northern hemisphere, Nightingale offered the clearest patch of regolith available. But clear was a dangerously relative term. The target site was roughly 16 metres in diameter, a fraction of the original safety requirement, and was encircled by building-sized boulders that loomed like sentinels ready to crush the spacecraft if it drifted even slightly off course. To land here was to thread a needle while wearing boxing gloves millions of miles from Earth. The descent required a level of autonomous precision never before attempted in deep space, because radio signals took over 18 minutes to travel between Earth and Bennu. Real-time joystick control was physically impossible. The spacecraft had to fly itself. The engineers programmed a complex choreography known as match point. OSIRIS REx would have to leave its orbit and perform a series of calculated burns to synchronize its velocity with the spinning asteroid matching its rotation exactly to hover over the landing zone. Before the final strike, the team executed 2 heart-stopping rehearsals to prove the guidance systems could handle the challenge. In April 2020, they brought the craft down to 65 metres. In August, they pushed it to 40 metres. Each time, the onboard computers successfully navigated the treacherous gravity well. But on October 20th, 2020, the rehearsals ended. As OSIRIS REx began its slow, perilous drift toward the crater floor, it angled its solar panels upward into a Y shape to protect them from the jagged terrain. The checkmate moment had arrived. As OSIRIS REx reached the climax of its descent, the onboard computers executed the final commands. The spacecraft extended its robotic arm, the touch-and-go sample acquisition mechanism, tagsome, like a heron stretching its neck to strike. The plan was simple: gently tap the surface for 5 seconds, fire a burst of nitrogen gas to stir up the dust, capture the material and then back away. The engineers expected resistance. They expected the surface of Bennu to behave like a sandy beach firm enough to push against. But in the alien environment of microgravity, intuition is a dangerous thing. At the precise moment of contact, the reality of Bennu's physics revealed itself with terrifying clarity. When the tagsome head pressed against the soil, it did not find solid ground. It found a void. The surface offered zero resistance. There was no crunch of impact, no pushback from the regolith. Instead, the sampling arm punched through the surface layers as if they were made of smoke. To the horror of the mission team analysing the data later, the surface of Bennu behaved not like rock, but like a fluid. It was a granular fluid, a state of matter that exists in the twilight zone of physics, where gravity is too weak to bind particles together. On Earth, gravity compresses sand into a walkable surface, creating friction and cohesion. On Bennu, where the gravity is barely a whisper, the rocks and dust are held together by nothing more than the faintest of Van der Waals forces. The asteroid was essentially a loosely packed ball pit floating in a vacuum. The spacecraft didn't land. It began to drown. The tagsome arm plunged nearly half a metre deep into the body of the asteroid within mere seconds. The solid ground was a mirage. Beneath the crust was a labyrinth of empty space and floating debris. If a human astronaut had attempted to step onto the surface of Bennu at that moment, the result would have been the stuff of nightmares. They would not have stood on the surface. They would have sunk, instantly swallowed whole by the asteroid like a traveller stepping into quicksand, vanishing into the dark, churning belly of the rock. The spacecraft continued to sink its momentum, carrying it deeper into the trap. It was arguably the most dangerous moment of the entire mission. The probe was being absorbed by the very target it sought to study. It was only the spacecraft's pre-programmed survival reflex that prevented a total catastrophe. Just as it was sinking, the onboard computer triggered the backaway maneuver. The thrusters roared to life, fighting not against gravity, but against the inertia of the sinking ship. In the midst of this slow-motion drowning, the sampling head executed its primary command. A bottle of high-pressure nitrogen gas fired from the arm designed to agitate the surface and drive regolith into the collection chamber. On a solid world, this would have kicked up a polite cloud of dust, but inside the fluid dynamics of the rubble pile, the gas burst acted like a depth charge. The explosion of gas didn't just stir the pot, it obliterated the landing site. With no gravity to hold the rocks down and no friction to keep them in place, the blast displaced an estimated 6 tons of material. It gouged a massive crater into the face of the asteroid, catapulting rocks and debris in all directions. Simultaneously, the spacecraft's thrusters roared into overdrive, burning harder than at any other point in the mission to arrest the vessel's sinking momentum and drag it away from the expanding cloud of shrapnel. OSIRIS REx clawed its way back into the black, leaving a scarred battlefield behind it. Safely away from the surface, the mission team commanded the spacecraft to spin. They needed to measure the change in inertia to calculate the mass of the sample collected. But before they could even finish the check, the cameras revealed a new crisis. The heist had been too successful. NASA had hoped for a modest 60 grams of material. Instead, the collector was stuffed with anywhere from 400 grams to over a kilogram of rock and dust. The collection head was so full that it was literally bursting at the seams. A rock had wedged itself into the mylar flap designed to seal the canister, jamming it open. Through the camera lens, the team watched in horror as their precious cargo began to drift away. The sample was hemorrhaging into the void. Small particles of the primordial solar system were floating out of the jammed flap, lost forever to space. The leisurely plan to measure the sample mass was instantly aborted. There was no time for physics experiments. The team had to stow the leaking collector head into the return capsule immediately. It was a race against time to seal the vault before the treasure simply floated away. With the precious cargo finally sealed inside the return capsule, OSIRIS REx turned its back on the asteroid that had almost consumed it. On April 7, 2021, the main thrusters ignited, initiating the long silent cruise home. For the next 2.5 years, the spacecraft became a ghost in the machine of the solar system, traversing a staggering 1.9 billion kilometers across the void. It was a period of quiet vigilance, a stark contrast to the chaotic violence of the collection event. The math had to be absolute. The navigation team wasn't just flying a ship, they were aiming a bullet at a moving target from the other side of the solar system. On September 24, 2023, the moment of truth arrived. As the blue marble of Earth loomed large in the sensors, the spacecraft executed its final delivery command. At a distance of 100,000 kilometers, roughly a quarter of the distance to the Moon, OSIRIS REx released the sample return capsule, sending it spinning into the dark. Immediately after the release, the main spacecraft fired its engines to divert its own trajectory, skipping past Earth to begin a new solitary mission. The capsule, however, was committed. It was now a ballistic object with no propulsion and no guidance, hurtling toward a specific 600 square kilometer patch of sand in the Utah desert, an area roughly the size of the city of Chicago. The margin for error was non-existent. If the entry angle was too shallow, the capsule would bounce off the atmosphere and be lost to deep space forever. If it was too steep, the heat would incinerate the history inside. The entry interface was not a flight, it was a collision. The capsule slammed into the upper atmosphere at a staggering 43,000 kilometers per hour. At this hypersonic velocity, Mach 35, the air molecules ahead of the blunt spacecraft simply could not move out of the way fast enough. They were compressed instantaneously, transforming the tenuous gas of the upper stratosphere into a shock wave as hard as concrete. The capsule wasn't cutting through the air, it was being crushed against it. This was the atmospheric anvil. The kinetic energy of the fall was violently converted into thermal energy, wreaking havoc on the capsule's exterior. The temperature spiked to a blistering 2,700 degrees Celsius, roughly half the surface temperature of the Sun. The air around the craft was ripped apart at the atomic level, turning into a sheath of superheated plasma that glowed with the intensity of a falling star, visible to infrared trackers on the ground below. Between the primordial dust and this solar-grade inferno stood a single line of defense, the Picker Shield phenolic-impregnated carbon ablator. This material is a masterpiece of sacrificial engineering. It is designed to die so the mission can live. As the heat intensified, the shield didn't just block it. It absorbed it and burned away. In a process called ablation, the outer layers of the shield shard melted and vaporized, carrying the lethal heat away from the spacecraft in trails of superheated gas. It was a calculated suicide of material, removing more than 99% of the vehicle's immense kinetic energy. Inside the eye of this firestorm, the physics of deceleration reached brutal levels. The rapid braking against the atmosphere generated a crushing deceleration force of 32 Gs. To put this sheer violence into perspective, a standard astronaut endures about 3 Gs during launch. A fighter pilot in a pressurized suit might briefly withstand 9 Gs before risking death. At 32 Gs, a human body would not merely lose consciousness, it would suffer catastrophic internal trauma as blood became as heavy as lead and organs collapsed under their own weight. Yet amidst this external chaos, the screaming plasma, the ablating shield and the crushing gravity, the engineering held the line. The Pika shield performed its duty with absolute perfection. While the exterior burned at 2,700 degrees, the interior of the sample canister remained a sanctuary of calm maintained at a temperature below 75 degrees Celsius. The history of the solar system was safe cradled in a cool dark box, while the shell around it fought a war against the laws of aerodynamics. As the capsule punched through the lower atmosphere, the violence of re-entry finally gave way to physics of a gentler kind. A couple of minutes after the peak heating phase, the drogue parachute deployed, snapping open to stabilize the tumbling craft for the remainder of the descent. At an altitude of about 16 kilometers, ground-based radars locked onto the falling beacon, tracking it with pinpoint accuracy to within 10 meters of its predicted path. For the final kilometer and a half, the main parachute unfurled, transforming the terrifying ballistic fall into a leisurely drift. The capsule, which had crossed the solar system at speeds defying imagination, slowed to a mere 18 kilometers per hour, roughly the pace of a cyclist on a flat road. From the moment it pierced the atmosphere to the moment it kissed the ground, only 10 minutes had passed. But in those 10 minutes, the timeline of history had shifted. The capsule touched down softly on the rugged floor of the Utah desert, sitting amidst the scrub and sand like a visitor from another epoch. The silence of the desert washed over the scene, replacing the screaming roar of plasma. But the stillness was short-lived. After years of planning and rehearsals, the NASA recovery team swooped in by helicopter. They approached the charred vessel with the reverence due a holy relic. To ensure the sample was not exposed to Earth's environment, the capsule remained sealed, hooked up to a continuous flow of nitrogen. The odyssey of flight was over. The odyssey of discovery was about to begin. Securely transported to the pristine nitrogen-purged laboratories of NASA's Johnson Space Center in Houston, the capsule was finally ready to surrender its secrets. The initial disassembly seemed to promise an easy victory. When the curation team lifted the outer lid, they were greeted by a chaotic, beautiful mess, a splatter of dark grey rocks and dust coating the outside of the sample canister. This was the material that had leaked during the dramatic jammed flap incident at Bennu. Carefully collecting this bonus spillover, scientists found they had retrieved 70 grams of material. The irony was palpable. The debris that had escaped the main vault amounted to more than the entire original mission goal of 60 grams. Before they had even cracked the main seal, the mission was statistically a success. But the true prize, the pristine hermetically sealed core sample, lay inside the tagsome touch-and-go sample acquisition mechanism head. To get to it, the team needed to unfasten a ring of 35 screws holding the canister shut. 33 of them turned smoothly. 2 did not. The mission, which had conquered the vacuum of space, navigated orbital mechanics with surgical precision and survived the inferno of atmospheric entry, was suddenly brought to a grinding halt by the most mundane of earthly frustrations, a stuck screw. 2 of the fasteners refused to budge. The culprit was the asteroid itself. Dust from Bennu had infiltrated the threads, increasing friction and essentially cold welding the metal shut. It was a maddening paradox. After travelling 9 billion kilometers to bring this box home, the engineers were locked out, separated from the greatest discovery of their careers by a few millimeters of stubborn steel. The standoff that followed was a masterclass in high-stakes frustration. For 3.5 months, the curation team at Johnson Space Center found themselves engaged in a silent, slow-motion siege against 2 stubborn pieces of metal. The problem was not simply that the screws were stuck. In any normal workshop on Earth, a stuck fastener is a minor annoyance solved with a burst of lubricant, a power drill, or a pair of vice grips. But the tagsome head was not in a workshop. It was imprisoned inside a nitrogen-purged glove box, a sealed glass chamber constantly flooded with neutral nitrogen gas to prevent the asteroid sample from reacting with Earth's oxygen or moisture. This protective environment, designed to keep the sample safe, turned the extraction into a nightmare. The engineers were separated from their work by thick glass and heavy rubber gloves that dulled their sense of touch and restricted their movement. It was effectively like trying to pick a complex lock while wearing boxing gloves, knowing that a single mistake could ruin a billion-dollar investment. The physics of the jam were equally unforgiving. The screws weren't rusted, they were cold welded by the very subject of the study. Dust from Bennu had infiltrated the threads during the chaotic collection event. In the vacuum of space and later in the nitrogen box, these hard diamond-like particles created immense friction, causing the metal of the screw to seize against the metal of the fastener. NASA engineers couldn't simply force the screws. Applying too much torque could snap the heads off, sealing the canister forever. Using standard power tools risked generating heat or creating fine metal shavings that would contaminate the pristine asteroid soil. The room for error was zero. The team had to stop retreat and invent a solution from scratch. They retreated to the drawing board to design a tool that didn't exist. They needed a screwdriver capable of generating immense torque without slipping, made from materials that wouldn't chemically compromise the sample. After weeks of design and fabrication, they produced a custom multi-part tool made from a specific grade of surgical non-magnetic stainless steel. This super screwdriver was the hardest, cleanest key ever cut. Rigorous testing followed. The tool had to be proven safe in a rehearsal environment before it was allowed anywhere near the glove box. Finally, in January 2024, 3.5 months after the capsule landed, the team moved in for the final turn. Under the anxious gaze of the world's scientific community, the new tool bit into the stripped heads of the fasteners. The engineers applied the torque. The friction yielded. The screws turned. When the lid was finally lifted, the weight proved worth every second of the struggle. Inside the canister lay 51 grams of the darkest, purest material ever seen, pristine asteroid regolith, that had remained sealed since the moment it left Bennu. Combined with the 70 grams of bonus material collected earlier, OSIRIS REx had returned a total of 121 grams, more than double the mission's original requirement. The vault was open. The siege was over. Under the scrutiny of electron microscopes and mass spectrometers, the black dust of Bennu dissolved into a story much larger than a single asteroid. It revealed itself to be a cosmic genealogy record. Buried within the dark matrix of the sample, scientists discovered pre-solar grains, microscopic crystals that are quite literally older than the sun itself. These tiny flecks of diamond and graphite are the rarest of artifacts. They are interstellar immigrants that condensed in the cooling atmospheres of ancient dying stars billions of years ago. They drifted through the galactic void, surviving the harsh radiation of deep space before becoming trapped in the swirling cloud of gas and dust that would eventually collapse to form our solar system. To look at them is to look at the parents of our own sun. By analysing the isotopic signatures of these grains, measuring the specific weight of the atoms inside them, cosmochemists could reconstruct the biography of the stars that created them. The logic of stellar nucleosynthesis is absolute. Different stars forge different elements. Small and intermediate stars burn slowly, fusing hydrogen into helium, and eventually creating elements like carbon and nitrogen in their dying breaths. Massive stars, however, live fast and die hard, fusing heavy elements like silicon and iron before detonating in supernova explosions, creating even heavier elements in the blast. The forensic analysis of the Bennu sample delivered a shock. While researchers expected to find the chemical fingerprints of gentle red giant stars, they found an overwhelming signature of violence. The sample contained 6 times the amount of supernova dust than any other astromaterial ever studied on Earth. This discovery rewrites the prologue of our history. It suggests that the raw material of our solar system was heavily enriched by the cataclysmic deaths of massive stars. We're not living in a first-generation system. Our sun, our planets, and the atoms in our own bodies are recycled material shrapnel collected from a stellar graveyard. Bennu acted as the preservation vessel, keeping these delicate grains of stardust pristine, protected from the geological churning of planets, allowing us to touch the ashes of the stars that died so that we could live. The most profound revelation, however, was not about the death of stars, but about the genesis of life. For decades, humanity has debated whether the ingredients for biology were cooked up exclusively in the warm tidal pools of early Earth, or if they were delivered from the heavens. The Bennu sample provided a definitive answer. The starter kit for life was assembled in the dark vacuum of space long before our planet even cooled. Initial chemical analysis revealed that the asteroid is rich in carbon and nitrogen, the fundamental atomic backbones of all living things. But as scientists looked deeper, they found complexity that defied expectation. Amidst the dust, they identified 15 of the 20 distinct amino acids that serve as the building blocks for all life on Earth. These are the Lego bricks of biology, the essential components that string together to form proteins. Even more startling was the discovery of the genetic alphabet. The sample contained all 5 of the biological nuclear bases: adenine, guanine, cytosine, thymine, and uracil. These are the letters of the genetic code, the components of DNA and RNA. Finding them all in a single extraterrestrial rock proves that the instructions for life are not unique to Earth. They are ubiquitous, scattered across the solar system in cold storage, waiting for a hospitable environment to wake them up. Perhaps the most significant find was a delicate sugar molecule called ribose. In the hierarchy of biological complexity, the discovery of ribose is a smoking gun for the RNA world hypothesis. This theory suggests that before DNA evolved to become the master storage of genetic information, primitive life relied on RNA ribonucleic acid to both store data and drive chemical reactions. Since ribose is the R in RNA, its presence on Bennu suggests that asteroids could have delivered this crucial sugar to the barren early Earth, jump-starting the transition from dead chemistry to living biology. The surprises did not end with familiar biology. Researchers also stumbled upon a bizarre space gum, a strange nitrogen and oxygen-rich polymeric material never before seen in a meteorite. Under X-ray spectroscopy, this material appeared deposited in layers on grains of ice, and minerals resembling a chaotic primordial version of polyurethane. Combined with the abundance of hydrated clay minerals, evidence that Bennu's parent body once harboured liquid water, the picture is complete. Bennu is not just a rock, it is a frozen package containing water organic scaffolding, genetic letters, and energy sources like glucose. It confirms that we are not a miracle of isolation. The recipe for life is written into the very geology of the solar system, and asteroids like Bennu are the delivery vessels that carried those seeds to our shores. For the return capsule, the journey ended in the quiet Utah desert. But for the mothership, the drop-off was not a retirement, it was a pivot. Roughly 20 minutes after releasing its precious cargo above Earth's atmosphere, the OSIRIS REx spacecraft fired its thrusters to divert its trajectory, narrowly missing our planet to slingshot itself toward a new target. The Egyptian heron has delivered its life-giving soil. Now it flies off to confront a monster. Its destination is the asteroid Apophis, named after the ancient Egyptian serpent of chaos, the mythological destroyer of light and order. This naming is not entirely melodramatic. Apophis is a 370-metre-wide beast that has long haunted the nightmares of planetary defence experts. In 2029, this stony serpent will make a pass by Earth so close within 50,000 kilometres that it will be visible to the naked eye skimming just above the orbit of our geostationary satellites. It is a rare, close encounter with a potentially hazardous object, offering a unique opportunity to study how Earth's gravity affects a rubble pile asteroid as it swings by. To reflect this bold extension of its life, NASA has stripped the spacecraft of its old title. It is no longer OSIRIS REx. It has been rechristened OSIRIS Apex OSIRIS Apophis Explorer. Starting in June 2029, the probe will begin an 18-month campaign to stalk Apophis, mapping its surface and analysing its chemical makeup. And just like at Bennu, it will get personal. The spacecraft will repeat its signature manoeuvre, dipping to within 16 feet of the surface and firing its thrusters to blast the asteroid with gas stirring up the rocks to reveal what lies beneath the skin of the Chaos Serpent. The return of the Bennu sample is not merely the conclusion of a technical mission, it is the closing of a philosophical circle. For years we looked up at the night sky and wondered where we came from. Now for the first time we have reached out, grabbed a piece of the sky and brought it down to Earth to confirm the answer. The black dust sitting in the nitrogen-purged cabinets of Houston tells a story of profound connection. The presence of water-soluble phosphates and hydrated clays paints a vivid picture of Bennu's past. It suggests that this small rubble pile asteroid is actually a shard broken off from a much larger ancient parent body, a water-soaked mud ball, or perhaps an ocean-bearing protoplanet that existed billions of years ago. This lost world may have resembled the icy moons of Enceladus or Europa, harbouring hydrothermal vents and active geology that churn these ingredients together in a warm, watery cradle. This connection is visceral. The mineral serpentine found in the sample mirrors the rocks found at Earth's mid-ocean ridges where new crust is born from the mantle. The pyrrhotite is the same iron sulfide found near our own hydrothermal vents. The phosphates are the backbone of our DNA. In the most literal sense, the OSIRIS REx mission did not travel to an alien world, it travelled to our ancestral home. It has confirmed that the boundary between Earth and space is an illusion. We are not inhabitants of the universe, we are made of it. The carbon in our cells, the nitrogen in our DNA, the iron in our blood, and the water in our tears, all of it was forged in the hearts of ancient stars and delivered to Earth by asteroids like Bennu. We are stardust that has awakened. We are an arrangement of atoms that has organized itself into complex beings, capable of building starships, calculating trajectories, and reaching back into the void to touch the very dust from which we sprang. The sample from Bennu is a mirror. In studying this ancient chaotic debris, we are not just learning about the solar system's past, we are finally meeting ourselves. For the return capsule, the journey ended in the quiet stillness of the Utah desert, but for the mothership, the drop-off was not a retirement, it was a pivot. Roughly 20 minutes after releasing its precious cargo above Earth's atmosphere, the OSIRIS REx spacecraft fired its thrusters to divert its trajectory, slipping past our planet with a calculated burst of fuel and slingshotting itself back into the black for a new crusade. The Egyptian heron has delivered its life-giving soil. Now it flies off to slay a beast, its destination, the asteroid Apophis, named after the ancient Egyptian serpent of chaos, the mythological destroyer of light and order. This naming is not entirely melodramatic, as Apophis is a 370-metre-wide rocky monster that has long haunted the nightmares of planetary defence experts, and in 2029 this stony serpent will make a pass by Earth so terrifyingly close, within 32,000 miles, 50,000 kilometres, that it will be visible to the naked eye, skimming closer to us than our own geostationary satellites. To reflect this bold extension of its life, NASA has stripped the spacecraft of its old title, rechristening it OSIRIS Apex, OSIRIS Apophis Explorer. Starting in June 2029, the probe will begin an 18-month campaign to stalk Apophis, mapping its surface and analysing its chemical makeup, and just like at Bennu, it will get personal by repeating its signature manoeuvre, dipping to within 16 feet of the surface and firing its thrusters to blast the asteroid with gas, stirring up the rocks to reveal what lies beneath the skin of the Chaos Serpent. While the spacecraft hunts the future, the sample it left behind has rewritten the past, for the return of the Bennu regolith is not merely the conclusion of a technical mission, but the closing of a philosophical circle. For millennia, humans have looked up at the night sky and wondered where we came from, and now, for the first time, we have reached out, grabbed a piece of the sky, and brought it down to Earth to confirm the answer. The black dust sitting in the nitrogen-purged cabinets of Houston tells a story of profound connection, as the presence of water-soluble phosphates and hydrated clays paints a vivid picture of Bennu's lineage, suggesting that this small rubble pile asteroid is actually a shard broken off from a much larger ancient parent body, a water-soaked mud ball, or perhaps an ocean-bearing protoplanet that existed billions of years ago. This lost world may have resembled the icy moons of Enceladus, or Europa, harbouring hydrothermal vents and active geology that churn these ingredients together in a warm, watery cradle. This connection is visceral, with the mineral serpentine found in the sample mirroring the rocks found at Earth's mid-ocean ridges, where new crust is born, the pyrrhotite matching the iron sulfide found near our own hydrothermal vents, and the phosphates serving as the backbone of our DNA. In the most literal sense, the OSIRIS REx mission did not travel to an alien world, but to our ancestral home, confirming that the boundary between Earth and space is an illusion. We are not inhabitants of the universe. We are made of it, for the carbon in our cells, the nitrogen in our DNA, the iron in our blood, and the water in our tears were all forged in the hearts of ancient stars and delivered to Earth by asteroids like Bennu. We are stardust that has awakened an arrangement of atoms that has organised itself into complex beings, capable of building starships, calculating trajectories, and reaching back into the void to touch the very dust from which we sprang. Meaning that in studying this ancient chaotic debris, we are not just learning about the solar system's past, we are finally meeting ourselves. This dialogue with the cosmos is far from over. In fact, the most exciting chapters have yet to be written. In a profound act of scientific foresight, NASA has not released the entire treasure trove for immediate study. Instead, nearly 70% of the Bennu sample has been hermetically sealed and locked away in a secure vault deliberately preserved for future generations. This archive is a gift to the scientists of tomorrow, researchers who are currently sitting in elementary school classrooms or who have not yet even been born. Just as we're now using advanced techniques to study Apollo moon rocks that were collected before the invention of the internet, the dust of Bennu waits for instruments that we cannot yet imagine and questions we do not yet know how to ask.